Hi, everyone. It's me, your boy, Dr. Lundholm. And today we're talking about section 13.2, limits and continuity of multivariable functions. We're getting here. We're doing calculus on multivariable functions where we're plugging in x and y. We've arrived at Calc 3. Um, this is a nice way to start off um, our lesson with the delta epsilon definition of limits for multivariable functions. Let's take a look at the high points here. Let f be a function mapping its domain, which is a subset of Rn, into R. Okay. To remind you, now we are looking at functions that take in multiple variables as inputs, and we are spitting out one variable as an output. And for the vast majority of the time in this class, our Rn is going to be R3. We're going to be working in three-dimensional space where we are mapping x and y values in the domain onto z values in the range. All right, we say that the limit of f as x approaches c is L, and write this limit notation, which is familiar. If for every number epsilon greater than 0, there's a number delta greater than 0, such that when f of x, and this x, you would want to treat it as like a vector. So maybe adding this notation just a little bit to remind us that this is multiple variables. Yikes, this is horrible. Sorry, guys. But yeah, this kind of an idea where x is multivariable, in our three-dimensional context, this vector x will look like an x value, a y value, and a z value, just so that we're all on the same page. Yeah, and that means the c value is also vectorish. It's got an x component, a y component, a z component. Okay, so for every epsilon, there is a delta such that the outputs are bounded by some number epsilon whenever x, and this is maybe not the greatest notation. Let's go ahead and, this is again a vector, but it's let's go ahead and write the point xy minus a point c1, c2. It's really the distance between 2 points is less than delta. Right. So in this definition, we're talking about Euclidean distance. And what I think would be good right now is to take a look at some GeoGebra stuff to remind you of limiting stuff that we've looked at before, and then look at a picture of what is going on here. And I think it'll make more sense then. Okay. Actually, I think I just have them pulled up on Google Chrome. Let's see. Sorry, Zoom, get out of here. Okay. So this is the epsilon delta definition of limit from calculus 1. We have one variable as an input variable. X is our input variable. Delta is associated with the domain. And epsilon's associated with the range. And y is our output variable. So one input, one output, delta epsilon. And this is what it looks like to have a region around C that is as big as delta, and this is a region around L with, a radius of epsilon. Okay. This is what we talked about in the last section when we were looking at vector valued functions. We have a vector valued function r of t with one input, and that input is t. And this function actually has a three-dimensional output. So in the delta region, one-dimensional. In the epsilon region, we have a three-dimensional. But in each case, delta is like the radius for how far away you would get from a certain point A. And epsilon is like a radius. Here, since we're working with a three-dimensional output, this epsilon looks like a sphere. And in general, we call these things like epsilon balls or delta balls. In a three-dimensional sense, a ball looks like a sphere. In a two-dimensional scenario, a ball looks like a circle. And in a one-dimensional sense, just like we had before, a ball kind of just looks like the endpoints of an interval. So yeah, on a one-dimensional line, really, you have a ball surrounding a point if you've just created two endpoints of an interval. Okay, but this one-dimensional input, three-dimensional output, that's why the epsilon region looks like a sphere. On to what we're looking at today, where we've got a two-dimensional input and a one-dimensional output. Let's click this. Okay, the blue surface is our multivariable function. Our multivariable function is here. I guess it's called B in this scenario, but x squared minus y squared on top and x squared plus y squared on bottom. So that blue surface is our multivariable function. And the domain of our multivariable function is right here. When we look down the z-axis, we see the xy plane, and I have created a sequence of points that are on the multivariable function if you look in the z direction, but they form a circle in the xy plane. I arranged them in a circle because what we're doing when we do an epsilon delta definition of limit is, we're looking to decrease the distance between some point that we're interested in, C1, C2, and just general points lying around it. And our radius in the domain is delta. We want the distance between these 2 points to be less than delta. So when you're calculating Euclidean distance, it makes sense that the region looks like a circle, because a circle is something that has a constant distance away around a center point. So the idea of limit here is that there's going to be some constricting in, here's delta. There's going to be some constricting in the xy plane. And here we're taking the limit as xy goes to 0, 0. So we're approaching the origin. So this is what it looks like in the domain. This is the limiting process, getting closer and closer and closer in. Corresponding with this two-dimensional ball that is constricting, we've got some z values. So I plot z equals epsilon and z equals negative epsilon. Yeah, and like these are our error bounds. So at this stage, for our, z values of plus and minus epsilon, when epsilon's 1.8, all of the function values corresponding to a circle in our domain surrounding the point that we're interested in, yeah, all of these function values are within our our epsilon bounds, and things look great right now. The definition, though, requires that for any epsilon, we should be able to find a delta that works. So that means we should be able to shrink epsilon arbitrarily small. And if I shrink epsilon down to 1/2, you can see that no matter how much we change delta, I guess I'll just let that, it's getting bigger, but it'll get smaller soon. No matter how much we change delta, notice that we always have some of those function values outside of the epsilon bounds that we want. This is a scenario where the limit's not going to exist at the origin, at x equals 0 and y equals 0, because we've got so many different distinct z values. And actually, here, if we freeze it really close, you can see that depending on which path we take towards the origin on the surface of this function, we can really reach any z value in between 1 and -1. But this is an instance where the limit doesn't exist, because no matter how small we make our circle in the xy plane, we can make it all the way down to 1/10. We're always, those small circles worth of points in the domain are going to correspond to function values that are outside of the epsilon bounds that we wanted to have. Let's go ahead and take a look at this more analytically. We'll, look at the notation again. All right, so definition there. Let's look at example 1. Example 1's asking us to determine whether this function, the one that I was just showing you, has a limit at the point 0, 0. And note that this isn't necessarily defined at 0, 0, because if you make everything 0, you just got 0 over 0, and that's in indeterminate form. Yeah. So yeah, there's not technically a function value at 0, 0. When we are looking to determine whether a function has a limit, there's basically going to be two things that we would like to prove. Either we want to prove that a limit doesn't exist, and this is actually one of the easier things to do if we can do it generally. So yeah, if we think that the limit might not exist, all we have to do is find two paths where the limit's not the same. Basically, we're constructing a counterexample to the limit claim. And so that's actually what we're going to do in example 1. But, for the sake of having a good overview of the different types of, limit proof techniques, while that's the way to prove that a limit doesn't exist, proving that a limit does exist would either, one, be plugging in the point we're approaching. I mean, if it's possible to take the limit as, xy goes to 0, 0 of some kind of a function, and everything just plugs in nicely and you get a value at the end, just like in calculus 1, that's fine. We can handle that. And just like in Calculus 1, sometimes it requires a bit of algebra to, get this function into a form where you're not in a 0/0 scenario. So that's what we'll look at in example 2. And then this is the one that you really don't want to have to do because it can be long and tedious. We will take a look at one of it, an example of this, but actually using a delta epsilon argument, that'll happen in example 3. And generally what that means is you want to find delta as a function of epsilon. So yeah, I guess you want to define delta as a function of epsilon, which seems backwards because, delta is associated with the domain, epsilon's associated with the range, but the way the proof goes is that you want to be able to make epsilon arbitrarily small. So that's actually more taking on the role of an input in the limit argument. And then the delta is kind of your output telling you exactly how large or small you want your circle to be. So we're going to take a look at that soon. Let's go back up to example 1 and prove that a limit doesn't exist. For this one, I hope you don't mind that I'm being lazy and I'm just leaving my writing here. And if you need more time to write it down, please feel free. But the idea here is that because we're not in just a one-dimensional input and one-dimensional output scenario, where in this kind of a scenario, we're really only concerned with the possibilities of a limit from the left and a limit from the right. But since we are now in a multivariable context and our domain, I'm actually going to get rid of these because they're in the way right now. Since we're in a multivariable context and our domain is two-dimensional, there are actually an infinite number of paths that we could take towards the origin. We could travel along the line y equals x. We could travel along the line y equals -x. We could travel along the x-axis, the y-axis. There's a whole lot of options available to us. I think the first thing that I do is travel along the x-axis, which is y equals 0. And so if I can find pretty sure I had a path. Oh, this one, doy. Okay. This one looks to be going along the x-axis. All right, so imagine that we're taking this path towards the origin. You can see that this path has a constant z value of 1. And that will show up when we do this analytically over here in the purple. So if we are taking the limit, and if I wanted to be thorough and actually show what we're trying to prove, it's the limit as xy goes to 0, 0 of the function x squared minus y squared over x squared plus y squared. And we're trying to hope to find a limiting value. So this is the overall problem that we're trying to solve. But in order to come up with a counterexample, what we're doing is trying to go along two paths. the first one, x-axis, second one will be along the y-axis. Those are just really easy ones to follow because that just means making y equal to 0 in this scenario and x equals to 0 in this scenario. And you can see when we treat y equal to as equal to 0, this more complicated rational function just reduces down to x squared over x squared, which is equivalent to 1. And that's why we see a z value of 1 along that entire line. Very similarly, if we're just traveling along the y-axis, the z value is a constant -1 because when you plug in 0 for x and 0 for x, you just get -y squared over y squared, and that's equivalent to 1, or sorry, -1. And just showing that there are two paths that have different limiting values, different z values, is enough to say the limit doesn't exist, and we're totally done. One of the things that I haven't talked about yet, but is kind of fun to mention, is this is kind of an alternate way to look at the limit that we just did. Noticing that as we're considering a two-dimensional domain and we're looking at this delta ball in 2 dimensions that has a radius of delta, we've got a circle. Wouldn't it kind of make sense to look at this function in polar coordinates? Because polar coordinates describing a circle is just, hey, you've got a radius and it's a constant number. So r equals delta is a good polar description of this. So, thinking about what this function might look like in polar coordinates and making the substitution x equals r cosine theta and y equals r sine theta is something that you might actually think about doing. The writing's not updating. But in a 3-dimensional context, when you're using polar coordinates for the xy plane, and then you're tacking on a z value on top of that, there's actually a special name for this, and it's called cylindrical coordinates. Cylindrical coordinates. And so here you can see that I've made that substitution of r cosine theta and r sine theta. And there is a little bit of magic that happens here because you get r squared cosine squared theta minus r squared sine squared theta. And the r squareds cancel out, and you're just left with cosine squared minus sine squared. And there's a cool trigonometric identity, I guess a double angle identity, where that whole piece just turns into cosine of 2 theta. Why did I go to the bother of doing this? Well, this function is now a function of r and theta. And notice that r doesn't make an appearance in here at all. What we would be trying to do in this scenario is find a limit as r goes to 0 of this function of r and theta. And since r doesn't appear in the function, that piece is just not going to go to 0. And the result of cosine of 2 theta just means that as we let theta vary between 0 and 2 pi, cosine's going to be able to go in between 1 and -1 as many times as it wants to. And yeah, that's why we don't have a solid limit as r. And in this case, that's the radius of, in the polar coordinate system. Yeah, limit as r goes to 0. So I don't know, sometimes thinking about these limits in cylindrical coordinates is kind of a nice additional way to look at it. But again, looking at this, it means that the limit doesn't exist. Okay. Cool. All right. And I mean, the paths that we chose here of y equals that, or yeah, of the x-axis and the y-axis were not necessarily special. They were just convenient. I think I chose 2 points on this and made a line in between them as well. So notice that like we could find lines that approach different values other than 1 or -1 if we travel along lines with a different slope in the domain. Okay, so that's cool. Limit doesn't exist because we don't shrink down to just one z value. Yep, and now we're going to look at some algebra. Just instead of showing that the limit doesn't exist, we'll show that a limit does exist. We'll do that soon, and then we'll use the delta epsilon argument, and that'll be great. As a quick aside, here we have limit laws, and these behave like you would expect them to. The limit of a sum is the sum of those individual limits. These all work like you would hope. Basically saying that when you transform a function and take the limit of that transform function, it's the same as, transforming that function after you've already taken the limit of the original one. So yeah, limit laws are a thing. They're especially useful when you're not given an explicit formula for the function that you're trying to use, but maybe they're just asking you to combine two different functions together based on some limits that you already have. Anyways, example number 2, we get to just plug the values in and get an answer. So again, we're taking the limit as xy approaches 0, 0 of this function where we've got xy minus y squared over the square root of x minus the square root of y. And if you were going to try to plug 0, 0 in right off the bat, you would get a bunch of zeros on top, and you'd get the square root of 0 minus the square root of 0 on bottom, and you'd be in a 0 over 0 situation, an indeterminate form, and you'd be out of luck. But coming to the rescue is this conjugate over here. So we look at our denominator, we've got the square root of x minus the square root of y, and that's ugly. So we multiply by the conjugate over the conjugate of that, getting our difference of squares factor pattern so that we just get a nice x minus y in the denominator. But what's nice about this whole process is that we get a matching x over y in the numerator, or x minus y in the numerator. Those cancel, so that when we plug in the limit 0 for x and 0 for y, we just get 0, which is a real number, and that's a fine limiting value. So using the conjugate to, algebraically manipulate this function into something where we can just evaluate the limit, that's a thing. Should feel pretty similar to the kind of stuff that we were doing with limits back in Calculus 1. And again, this is the same type of thing. We're not approaching the origin anymore. We're approaching the point 1, 4 in the domain. But the same thing's happening. This time, again, we are kind of looking to get rid of the radicals when we can. So we multiplied by the conjugate of the top here. And eventually things shake out so that this factor in the numerator and this factor in the denominator cancel out, so that we're left with something where we can just plug in 1 and 4 for x and y and get a real number. But yeah, that is, even though that looks, kind of tedious, it's by far the easier way to prove that a limit does exist. When you can just substitute in the point, that's great. And really this conjugate way of manipulating things is the only way that they kind of point out here. But, it would be possible to factor the numerator of a rational function and factor the denominator and possibly get some factor that would cancel out on top and bottom as another viable way to use algebra. But yeah, so that's the thing. Example number 3, we're going to take a look at proving this using a delta epsilon eventually. But first, I'd kind of just like to take a look at this and show you how it's a little bit different than example number 1 that we looked at before. We've got a rational function over a rational function again, so that looks pretty similar. We're approaching the origin again. And if we were going to plug in 0, 0, we would have 0 on top and 0 on bottom. So we're in a pretty similar scenario there. But notice if we, this is not necessarily part of the curriculum, but it's just something that I kind of think it would be, it's just a nice alternate way to think about things and get a different perspective. If we were to translate things into cylindrical coordinates, where x is r cosine of theta and y is r sine of theta, again, we're going to get some things that cancel out on the top and bottom. We would have r cubed on top because we'd have an r squared coming from this first factor and an r coming from over here. And so when we reduce this fraction, we would get 5r cosine squared theta sine theta. And notice that when we take the limit as r goes to 0 of this multivariable function, as r goes to 0, everything else here will go to 0 because 5 is just a constant number. The cosine squared of theta and sine, those would both be bounded above by 1 and bounded below by -1. So yeah, this r is going to dominate everything else. And as it goes to 0, the entire function is going to go to 0. So unlike the scenario up above, where shrinking r to 0 doesn't really change cosine of 2 theta at all, that can still go from 1 to -1 however it wants. When we shrink r to 0 down here, we are approaching 0 as a y or a z value. And so we do expect the limit to exist here. And so now let's go, out of polar coordinate land, back into Cartesian coordinate land. And this first part, what we're doing is something that you can do if you think the limit might exist, substituting in y equals mx to get a line with a slope of m that goes to the origin, that can be a handy way to, see if multiple examples all agree all at once of many different paths that could approach 0, 0. But this is not necessarily a proof that the limit exists, as we will see at the end of this lesson, even though we would be testing, infinitely many paths towards the origin here, along, a bunch of different lines with slopes of whatever we want m to be. Even though all of these work out to be 0 in the end, because as we make x go to 0, the numerator goes to 0, the denominator just stays 1 plus m squared, and since the numerator is 0, the whole fraction 0. Yeah, even all these lines exist, it doesn't necessarily guarantee that the overall limit exists. And I'll show you that soon in the bonus example at the end. I want to get a picture here. For some reason, the link's all the way down here at the bottom. Okay. There we go, computer. Let's get rid of these epsilon bounds real quick. Okay, so looking down the z-axis, here's our domain. The only reason that this looks weird is because we've got z values getting really high or really low, and those are getting cut off. But yeah, we're looking at the xy plane. We have our delta ball. And right now I have it defined as a function of epsilon, but that's for later. Come on, delta. All right, hold up. Let me make delta into a slider. Let's make it 0.1 as a min and 4 as a maximum. And slow show. Yeah, there we go. Show the slider. There we go. So now we can change that delta radius in the domain. We also have the line y equals mx here for funsies. That's our blue line with those blue points. Okay. And what this work that we just looked at shows us that when we make the substitution y equals mx, and we track as x goes to 0 along that path, the z value goes to 0. So in the context of our graph, as we change that blue line, the slope, the points on the function where we put in those lines y equals mx in the domain, all of those z values that are along the function still make a line. And as you get closer to 0, 0, yeah, all of those lines have a z value of 0. No matter what slope you're inputting in. And it's kind of cool to watch, that line of blue dots shift around. But notice the z value is always 0. It's always going through the origin. And from top down, this just looks like changing the slope of a line. All right, so the fact that all of those approach 0 should give us some confidence that probably the overall limit is 0. And that is when we get to the epsilon delta definition to prove it for realsies. So the idea is for any epsilon, and now I'll bring these planes back in and I'll get rid of the sequence of points. For any epsilon, right now epsilon's equal to 5. If epsilon's 5, a delta of 2 works perfectly fine, because whenever we're putting in points that have a radius of 2 from the origin in the domain, all of the z values are within 5 units of 0 in the z direction. So that's perfectly fine. The problem arises when we shrink epsilon, and we want to be able to shrink epsilon to an arbitrarily small number. But yeah, if we shrink epsilon down, well, now we've got z values that are outside of our epsilon bound, and we need to shrink delta correspondingly. And I guess, if we shrink delta down to 0.3, we've got it again. But instead of doing this, chasing game where we shrink epsilon and then shrink delta again, if we can define delta as a function of epsilon, they will just shrink or increase together, and we'll never have to worry about it. And that's the idea for, what we're trying to accomplish with this epsilon delta thing. Okay, so here's the notation. Again, we've got the distance between an arbitrary point xy and the point in the domain that we're approaching, 0, 0, should be less than or delta, and then the difference in z values should be less than epsilon. And again, just to remind you, the condition that this is the distance between 2 points is this distance formula that we're accustomed to. It's just the Pythagorean theorem. So we want to define delta as a function of epsilon so that they vary together. It would be great if we could make the epsilon part look more like the square root of x squared plus y squared, because if we can do that, then we can compare delta and epsilon more directly and hopefully define delta as a function of epsilon. So that's the idea behind this string of work. Even though this is kind of a mess to follow, I tried to highlight the important parts so that we could follow it. But I want you to continue paying attention. But am I going to ask you to do this on your own very much? No. Am I going to ask you to do this on a test? No. But still, it's good for us to try to do this hard thing. Anyways, what we're doing is we're looking at, this is the epsilon inequality, where we've got f of xy minus 0 is less than epsilon. So we're looking at this, and we're trying to make the epsilon part look like square root of x squared plus y squared so that we can compare delta and epsilon nicely. So this is our function, that's 0. And our first move is to take the absolute value signs that are on the outside and try to reduce the number of absolute value signs that we are using. Now, the 5x squared and the x squared plus y squared part, those are always going to be positive. And so it's a little bit redundant to put the absolute value signs around them. So that's why the absolute value signs are dropped over here in the next part. We do keep the absolute value sign on y though, because y can be positive or negative depending on what values we put in. And notice this is an equal sign. So nothing has changed as far as the value. But we are going to make a small sacrifice here and do a less than or equal to sign, because what we're comparing is this fraction, x squared over x squared plus y squared, and if you think about that, for any values x and y, think about whether, I don't know, what this fraction would be compared to 1. Will it be smaller than 1 or bigger than 1? The answer is smaller than 1, because x squared and x squared will be exactly the same here. And so either y could be 0 and you would have exactly 1, or if y is bigger than 0, you're going to have a bigger denominator than your numerator. And so what we can do is say that this part of the function is always going to be less than or equal to 1. And just say that now we have this is less than or equal to 5 times the absolute value of y. Now, the absolute value of y also has a cool alternate definition as the square root of y squared. That's how we get to the next part. And we can make yet another substitution in here where we add in x squared. Now, this part might look weird, but we're comparing, let's go orange. We're comparing the square root of y squared, and why should that always be smaller than the square root of x squared plus y squared? For a very similar reason to this less than or equal to thing that we had before. If x squared is equal to 0, then these would be exactly the same. But if x is anything other than 0, this square root will be bigger than this square root. And now we've gotten to something where we've got the square root of x squared plus y squared, which is delta, because that's the distance from the origin to a certain point xy. And now that we've got a delta, a thing that looks like delta coming out of the inequality, like the absolute value thing that started off defined in terms of epsilon, we've made a connection between epsilon and delta such that now we can just substitute in delta and we have a relationship between delta and epsilon, so that if we make the substitution of 5 times delta equaling epsilon, or if we want to arrange this into delta as a function of epsilon, delta equals epsilon over 5, we can go back to GeoGebra. Push a backspace, pull this out so that we can find an epsilon, divide that by 5, boom. And now, instead of doing the whole rat race where we, change both of them independently, notice that if delta's equal to epsilon over 5, we get a cool relationship where, the circle in the domain's always shrinking fast enough to keep up with the shrinking z-value interval, so that we always stay inside. And notice that it's not a perfect fit. It's a little bit conservative, but that's fine. And that's arising out of the fact that we had a couple less than or equal to signs in this line of reasoning. But yeah, once you figured out delta as a function of epsilon, you've got it. So that's good. It'll keep our delta ball small enough so that our corresponding z-values stay safely within the epsilon error bars. Oh my gosh, why are we doing all this limit stuff? Again, limits are fundamental to calculus. because, behind the scenes, even though we're not going to use the limit definition of derivative or the limit definition of integral for very long, because it's just so much more practical to work with rules like the chain rule and all that good stuff. Limits are really what undergird all of calculus, so it's good for us to look into this. And this is as rigorous as it would get in terms of yeah, like even if you were taking a class like real analysis, this is the kind of thing that is more heavily emphasized, and proofs are more heavily emphasized, and you make calculus all that much more rigorous. Yeah, anyways, we are going to take a break from that and continue on, making a note of continuity. The definition of continuity is much like what we've seen before. We're taking the limit as x approaches some point C. And again, this is, you would think of x as like a vector of an x value and a y value, and C having an x value and y value. But yeah, as long as the limit equals the function's value, then we're continuous at a point. So that's cool. The definition of continuity. And if we wanted to look and determine where each of these functions is continuous, basically we'd be looking where could this function be undefined. For the bottom part, we wouldn't want the denominator to equal 0. Which means that we wouldn't want x squared plus y squared plus z squared to equal 9, which we've seen before as the function, or well, this isn't necessarily, I mean, it would be a 3-variable function. What we've seen this is as a quadric surface. That's a sphere of radius 3, right? So as long as our point xyz doesn't fall on the surface of a sphere of radius 3, then it would be, part of the domain, and we could talk about this being continuous at any of those other points. So this is a little departure of the normal thing that we've been doing. This is a multivariable function that takes in 3 input values and would output one output value. Maybe you'd call it W or something like that. So that one's fine, a little weird. We do the same thing down here and think about where this would equal 0. It's never going to equal 0 because x squared and y to the 4th would always be positive, and you're always going to be, or it would be non-negative at least. You're adding 1 to it, so the smallest this denominator is going to be is 1. So yeah, this one is always continuous. This one's continuous unless you're at a point on a sphere of radius 3 in the domain. Okay, that's continuity. It's checking to see whether the limiting value equals the function value. And again, example 5 is along those same lines. We're looking at the function that we had done before with the lines and the epsilons and deltas. So we're looking at the same function from example 3, where the limit does actually exist and equals 0. But the new thing that we're concerned with here is continuity. And the question is, can we extend the definition of this function so that it's continuous everywhere? And remember, the only point that this would be discontinuous is if x and y are both equal to 0. And so if we plug that hole with the z value of 0 that corresponds to the origin, x equals 0 and y equals 0. If we plug it in with that point, then we have a function that's continuous everywhere, and we would just use a piecewise definition for this new function. Okay, so that's cool. Not a huge deal. This theorem is a composition of continuous functions as continuous. This is something that is really nice to have. It's the same kind of thing that we've relied upon in Calculus 1, but basically this means that, yeah, if we get functions that look more complicated, we probably want to consider the domain of, what values we're allowed to put in for our input variables, here x, y, and z. But since this is, an exponential function, and inside the exponent, it's just a polynomial. A polynomial is going to be continuous everywhere, and an exponential function will be continuous everywhere. So the composition of both of those things is continuous. This arctan thing, there's a little bit of a consideration whenever x equals y, the denominator of the fraction inside of arctan will have a denominator of 0. So you don't want x to be equal to y, but everywhere else, this thing will be continuous. So that's fine as well. Yeah, those last several examples about continuity, they're cool, but I brought in this bonus example. We can call this example number 7, but really it's problem number 27 from the homework, exercises. But I thought this function was really cool and demonstrates another algebraic technique for showing that a limit either doesn't exist or does exist. So what we're trying to do is showing that this function has a limiting value of 0 when the origin is approached along any parabola, but has any limiting value between -1 and 1 when we approach via this kind of curve, which is, kind of like a parabola, kind of like a cubic function. It's a cubic function kind of mashed up with a square root. And yeah, what this trick could be summarized is making a path. Let's say what we're doing is make a path in the xy plane so that the degree of the numerator, degree of the numerator and denominator match. Right now, if we look at this rational function, we've got x to the 3/2 power on top, we've got y to the 1 power, and if you were to multiply those, you could think about the total degree of the numerator kind of being like 5/2 maybe, but again, one's x and one's y, so it's not like directly that you could mash them together. And on the bottom, the degree is 3 for x and the degree is 2 for y. So they don't match right now in terms of numerator matching denominator. But you can get some really nice cancellations if you can make a smart substitution so that the numerator and denominator actually end up matching. So what the work that I have down here in blue is this first part where we're not necessarily being super clever. The degree of the numerator and the degree of the denominator are not necessarily going to match. But we will be able to find a limit. So if we plug in cx squared in for y everywhere, I don't know. For the first part, we've got 2x to the 3 halves power times cx squared all over x cubed plus cx squared squared. We combine what we have up on top to get 2c times x to the 7 halves, and then do a little bit of factoring on the bottom so that we pull the common factor of x cubed out and have x cubed times the quantity 1 plus c squared times x on the bottom. Now we realize that we could cancel out a factor of x cubed on top and bottom so that we're just left with x to the 1/2 on top along with 2c, and we get 1 plus c squared times x on bottom. Now plugging in the limit as x goes to 0 means that the top would be going to 0 because we'd be taking the square root of 0. And the bottom goes to 1 because this term will go to 0, but this one will still stick around. And that means that along any path, any parabola path, we're going to approach the point 0, 0. Let's go ahead and look at GeoGebra to get a little break before we do the other path. There we go. Okay. So this purple line is our quadratic path. And yeah, this C1 is the coefficient. But notice that if we look at the z values, as this quadratic path approaches the origin, the z values always approach 0. So if we were just to, test out an infinite number of parabolas here, we might be under the impression that this function would have a limit as we approach the origin, because we always approach the z value of 0. Notice though that, we're missing some stuff up here and we're missing some stuff down here as we use these parabolas to approach. So in the xy plane, this just looks like a parabola that's, being stretched or squished. But when we plug in the substitution y equals c times x to the 3 halves power, there's going to be some cool cancellation that goes on. Let me go ahead and zoom in a scotch. Here, if we plug this in, we still have x to the 3 halves, but when we multiply it times this x to the 3 halves, we're going to get x cubed on top. And when we square the x to the 3 halves on bottom, we're going to get another x cubed, so that when we pull out the common factor of x cubed, like last time, we have a factor of x cubed on bottom and a factor of x cubed on top that we can cancel out. And now all we're left with is an expression in terms of c. So the fact that x is going to 0 doesn't change this at all. But depending on the value of c that we could put in between 1 and -1, this will have a range of -1 to 1. So yeah, if we put in c equals -1, we would have a -2 on top, and we would have a +2 on bottom, which would give us an output of -1. And if we input 1 in for c, we would have, yeah, 2 on top and 2 on bottom, which would give us an output of 2/2, or 1 overall. And so we can see that as we change c here along this green curve, which, kind of looks like a parabola, but it's a cubic function that's been mashed with a square root function. So this is, yeah, a parabola with a 1.5 in the exponent rather than a 2. This is what happens when we change c here. Again, it's just stretching or squishing the same kind of function. But the behavior of this curve as you approach the origin is going to be vastly different than the parabolas that we just looked at. All right, so let's stop it up here at 1 and check out, hey, this thing has a constant z value, and that z value is always 1. Whereas, I don't know, if we let c change a little bit, notice that our z value is still constant, but it's not always 1. And that is contrasted with the corresponding parabola, where the parabola looks like it was up at 1 for a while, but then it takes a dive near the origin. And so, yeah, when you have mismatched degree on top and bottom, you can have that kind of a diving thing happening as x goes to 0. But when you plug in a curve such that the degree of the numerator and denominator match, you get rid of those variables, and all you're left with is a constant that you can change, and it won't change depending on whatever value of x that you put in, which means that the z value is going to be constant, and it's just only going to depend on c. So this is what it looks like, if we were going to put in basically 0 in, it does look like the limit would be 0. And here, if we stopped at c equals -2/10, it looks like maybe we're at a z value of, roughly 4/10, or -4/10. But the z value is always constant there, and that allows us to approach any value in between 1 to -1 that we want to along that path. And so this is what I was talking about earlier, that even if you get into a scenario where you take a bunch of curves and it always looks like you're approaching the same point, like earlier we had done it with not this one, where we approached using a bunch of different lines, and we were just changing the slope of those lines, and we were always along those lines approaching the z value of 0. In this problem, you can have an infinite number of parabolas that always approach the z value of 0, but when you change the parabola into something that has a 3/2 power, you no longer always approach 0. You can approach any value in between 1 and -1 that you want. So this definitely shows that the limit doesn't exist, and you would never know it if all you tried was parabolas, or even if all you tried was lines. Yeah, and I guess you might be, curious how I'm making these. What I'm doing is I'm making space curves like we've done in the past, parametrically defined, where the x value is equal to t. The y value here is c1 times t squared. So we've got that parabola thing going on. And then the z value is just the function evaluated at that point, t c1 t squared. So I'm, making space curves with the correct x, y, and z values that coordinate, a parabola in the xy plane to the function's output according to those x and y inputs. And we could do the same thing for a line. I don't know that I have it here real quick. Oh, I did make it. Okay. I guess there's a bunch of points. We could make it a space curve as well. Yeah, let's make it a space curve because we don't see the kind of tail end behavior when we've got all these discrete points. I was using the sequence function for that. Let's go ahead and make a space curve real quick. Curve. But if we were just going to make a straight line in the xy plane, we would want to use t. And then I guess I've made my slope c1 here. So c1 times t for the y value. Then we would want to use f of t comma c1 times t for that, the z value. And then say that our parameter is t, and we go from -10 to 10 for funsies. Boom. And now we have a line in the xy plane that we can change according to this. And I'm pretty sure that we come to a similar conclusion as to what the parabola does. Again, because the numerator and denominator of that rational function would be mismatched. Yeah, it's even a little bit weirder than the parabola if we look at the z values, but eventually it always does approach 0 in the end, no matter what slope you give to the line in the xy plane. So you'd come to the same conclusion if you were just trying a bunch of lines of different slopes. You really need to pick out this special kind of curve that makes the numerator and denominator have the same degree. All right. Well, that was fun, right? I think these true or false questions are the homework that I've assigned you for this section, so that's not going to be too bad. But the big ideas were that there is a delta epsilon definition of limit, and that I guess we should just hover in on this. That when you're looking at limits of multivariable functions, we've basically got 3 choices. One where we prove a limit doesn't exist by finding 2 paths where the limit doesn't exist, where they're not the same, and you create a counterexample. Or you can prove that a limit does exist using some algebra or using a delta epsilon argument. But this is hard. But yeah, I think that's it for today. Please go through and discuss any of that you want to. I hope you have a great day, and I'll see you tomorrow. All right, bye.